So I want to talk about this phenomena of noise-induced limit cycle and entanglement. So the core idea is that typically noise and loss are seen as detrimental things for stabilizing long-range correlations or persistent oscillations. But this doesn't always have to be the case. I'll discuss a small example in which the reverse happens. You need noise to get a limit cycle behavior and produce large-scale entanglement, which is not present otherwise. So this work was done with this master's student, Akash Kumar Kira, who is now a PhD student in CISA. So I'll dive straight into the model. So the model is just a two-site boson model. You have these two sites, 1 and 2. You have a normal hopping, coherent hopping, which is this Hamiltonian term. And you also have an incoherent process, which takes you from 1 to 2. Right? So this is just a one-way process. In this case, I'm modeling it by a Lindblad operator with some loss, with some rate of going from 1 to 2, which is this kappa. Right? And now this model clearly conserves the total number of particles, n. And you can have total of n plus 1 states because you can put all the n particles in 1 and have 0 particles in 2, or you can have n minus 1, 1, n minus 2, 2, and so on. So it has a fixed number of states, and therefore you can map it to a spin S with S equals n by 2, right? 2s plus 1 states, where the north pole will be the configuration n0 and the south pole is the configuration 0n. Right, so, and in terms of the spin model, the Hamiltonian Lindblad operator looks like this. And this particular model has been of interest for a long time in the quantum optics community and more recently in the many-body physics community. So this model itself is widely studied. This doesn't have any noise or fluctuations as of now. Now, to analyze this model, one way is to go to the classical limit, a very large number of bosons, which is also will mean that S is very large. And, and in that case, you will have these, the classical trajectories will have these three coupled equations. So you see that the kappa terms are trying to take Sz to minus 1. Sz, these are these normalized spin components. And these other two terms, here and here, are trying to, is the magnetic field along the x-axis, which is trying to rotate the spin about the x-axis. Right? So, okay, so that's the thing. And then you see that this total spin length is conserved. So the dynamics happens on a sphere. So I can just reduce it to these two angular coordinates, polar angle and azimuthal angle. Now, depending on kappa, this has two different regimes. So one is that when kappa is small, then the Hamiltonian, this magnetic field motion dominates and you get these periodic orbits. There is many periodic orbits here. And in particular, there's this giant, this great circle in the YZ plane, which in the theta phi plane looks like this rectangular orbit here. So this correspondence will be helpful later on. And whereas when the loss, this kappa dominates, then the thing goes to a fixed point close to the south pole. Right? So depending on kappa is less than 1 or greater than 1, you get these two types of behaviors and a bifurcation. But note that in this case, although there are many periodic orbits, they are not stable. So if you nudge it in the perpendicular direction, it will go to some other orbit. So there is no limit cycle as of now. Okay, so in the quantum case, again, you have these two types of behaviors. When kappa is more than 1, the quantum wave packet also goes very close to the classical fixed point and gets some finite spread because of the quantum uncertainty principle. And in the kappa less than 1 case, it doesn't oscillate forever like the classical point, classical motion, but instead the oscillations die out. So this is a quantum effect which eventually causes the oscillations to die out. The time to die out scales with S. So for very large S, this keeps continuing, this keeps oscillating forever. And so that phase has been called a time crystal phase. If you look at the wave packet in the steady state, if you wait long enough for it to reach the steady state, it reaches some broad distribution with weight over many classical orbits. Right? So that's the quantum model that has been studied already. Now, so now the part of adding noise. So what I do is I take this loss rate kappa and I vary it between two levels in a telegraphic noise manner. Right? So this is the particular noise realization. And so what you find from this is that starting from a point where the unnoisy case will not have any dynamics, the trajectory quickly goes to this great circle on the YZ plane and keeps winding around this great circle. So this is how it looks on the sphere. If you plot the components, you see that the X component dies out pretty quickly and then these things keep oscillating forever. So there is now an attractor. So starting from anywhere outside this great circle, you actually approach this great circle. And I think the reason is that for different values of kappa, the great circle is the only orbit that doesn't change with kappa. That is the only invariant orbit. Whereas the other orbits keep changing as you change the value of kappa. So the result of the fluctuation is to actually drive it. So it becomes a invariant orbit, and turns out that the dynamics also makes it an attractor. So it goes there. You see that the oscillation is not uniform. You can easily, that depends because the noise has two different rates. So you can correct for the phase winding. If you plot it as a function of the phase on the YZ plane, it looks like a uniform oscillation. That's the classical dynamics. Also, the thing it requires some fluctuation in the switch intervals. If you make it a periodic switching, it doesn't work. It's sort of limited to a finite set of finite area on the sphere. It doesn't go to this YZ circle. So the noise is useful. Now, what happens something similar happens in the quantum case also. So this was the thing before adding noise in the kappa less than 1 regime. This is the time crystal phase, where eventually the oscillations die out. So starting from the south pole here, you'll see that it sort of moves around this YZ circle, but then it eventually broadens and becomes a very sort of broad distribution with large fluctuation in Sx, for example. So this fluctuation in Sx becomes of the order 1 in the steady state. So this is the case without noise, but then if I add the same telegraphic fluctuation in the noise rate, you see that now the fluctuation has gone down. Instead of being order 1, it now becomes order s to the minus half. So for large s, it becomes classical limit. There is no fluctuation at all. And here, unlike the previous case, you'll see that it will not broaden out. It will sort of keep following this YZ circle. So for finite value of s, there will be momentary large fluctuations, as you will see in a moment. But then it'll again come back to this confined orbit and more or less keep rotating there. Okay, this is the steady state before switching and with switching. For the switching case, I have now averaged over different noise realizations. So you see this weight on the YZ circle with some higher weight here because it's non-uniform. So it spends more time around the point which is about to become a fixed point. Okay, and this is about, so fluctuation, this is I already showed. You can also connect it to entanglement because ultimately I started from a quantum model. So I can ask, so going back to this boson model of two sites, I can ask how much is the entanglement between these two sites as a function of time. And you see, so one way to calculate entanglement for mixed states like this is negativity. And you see that this also has a much larger scaling for the noisy case compared to the noiseless case. So noise is not only giving it stability, but also making it more entangled than otherwise possible. Yeah, so that's pretty much it. So the main finding is that fluctuating loss rate in this model produces limit cycle and entanglement. And I mean, this could be more general feature where you have some orbit which is invariant with respect to some rate, whereas the other orbits keep fluctuating. So whether it can be seen in more general settings is one thing we are interested in. We also found in other systems that noise can reduce the average loss rate or stabilize unstable fixed points. There are also some examples like that I didn't have time to talk about. And this sort of connects to related literature in sort of classical dynamical systems on what are called noise-induced transitions and stability, which has been studied for a long time now. Yeah. Okay, so thanks.
Thank you, Shovan. Questions?
What do you mean by the lousy system in your
lousy system?
Or lossy system?
Lossy, I just mean that it's not a Hamiltonian dynamic. So you need this incoherent part also from so if you think of it as two energy levels, then you have this spontaneous decay from one to the other level.
Does the time crystal survive noise?
Yeah, so the time crystal, you had many periodic orbits like this, right, in the classical case. If you add noise, what happens is that they eventually go to a limit cycle. So instead of having many periodic orbits which don't have any stability, all of them eventually flow to a particular periodic orbit, which now has become an attractive limit cycle. So in a way, it's more stable with noise.
Are these systems like self-averaging, meaning you average it over this telegraph noise, right?
Yes.
So if you just took one of them,
I think it would be. We haven't checked, but yeah, I think if you average the fluctuations over one trajectory, for example, I think we are finding similar scaling. I don't know whether it's exactly. We haven't looked into that deeply, but I think so.
I have one small question. So you pointed out the importance of noise for getting this orbit in the YZ plane.
Yeah.
So in the individual quantum trajectories also, we anyway have this stochastic noise.
Yes.
Like we don't need to vary the kappa.
Yeah.
Kappa itself is the noise strength
Yeah.
for those quantum trajectories.
Yeah.
So can you get some kind of stable limit cycle there?
No, actually, so you're talking about the quantum noise
Yeah.
that is at the level of individual trajectories, you
Individual
have the
quantum
stochastic term.
trajectories.
So in that particular kind of noise, I mean, which turns into diffusion eventually if you average over the noise trajectories. But you see in the average trajectory, there's a spread which scales like s to the half. So if you look at the individual trajectories, you see large fluctuations, right? So it doesn't stay confined. So you get fluctuations of the order of s to the half also at the level of individual trajectories. So actually you need a slightly different type of noise.
Okay, thanks. Okay, so we move on to the next speaker. Thank you. Sure.